So our topics today are going to be transmission losses, and we're going to begin a very important topic, although we will begin this and then drop it, and we won't pick it up until later. But it comes in. When we wrote the book, we thought it was important to put it right here at the front of this chapter. So remember I talked earlier that our friends, the economists, like to use the term marginal price as the first derivative of cost with respect to, in the case of a single generator, it's DFDP. So we're going to talk about the locational marginal. This is how the markets you get into economic dispatch. The markets use a system that's based on this LMP, and this was brought to the electrical engineering, power system engineering community, like I was part of for my entire career. This was brought to us by the economists. I can tell you, in the 1990s, there were people who who hated economists. I think literally. There was one fellow that worked here in Minneapolis for one of the organizations, and I remember him starting to talk to me at a conference here at the university. And I talked to him for a while, and I said, well, I need to go. And he followed me out of the room and down the hall ranting about economists. He used to say, hang all the economists. I don't agree. They brought a new way of looking at things, a new way of doing things, and I'll be very honest, they brought a new discipline to power system engineering. Now, fortunately, we power system engineers, put on my my Power Engineering Society hat, we had solved a lot of the basic problems that needed to be solved. And to get these LMPs, we had solved the optimal power flow problem, and as well as lots of other problems, so that the deregulation of the power systems could not have occurred, in my opinion, in the 1970s or 1980s, because the software, the solutions simply weren't there. But by the middle 1990s, they were there, and they were able to proceed. And MISO that operates here, there's a MISO office in Eagan, has use this technique and is sort of a backup to the MISO Center in Indianapolis. Okay, what I'm going to do now is we're going to talk about losses, and this is a topic that goes way back. I mean, power system engineers recognize that the transmission lines, losses. Us engineers know this is I squared R. You can't push a current through a transmission line without incurring some heating. That literally causes heat in the transmission line, and that heat is dissipated into the atmosphere. It's gone. It represents an inefficiency. It's only between 2 to 4% for the overall delivery of power at the transmission level. So it's not a lot, but think about it. Let's say Minnesota is a 10 GW. Okay. So what's 2%? That's let's see. Let's say 10 GW is 2,000 megawatts times 0.02. That's is that 40? Am I getting the decimal place correct? Yeah, 40 megawatts. That's a lot of power. Now, granted, it's not a matter of some particular power plant supplying it, although that could be the case. It's a matter of everybody supplying that much, but it represents an economic penalty. It's a loss. Note also that the transmission losses will mean that those transmission lines are heating up. And we're going to come back to this in the future when we talk about security, when you really overload transmission lines, which usually happens when you have an outage of a major transmission system resource, like a large transmission line, and the power goes down through other lines. It skirts around and goes through other lines. When that happens, the lines warm up. In 2003, we had a large blackout in the Midwest, starting in Ohio, northern Ohio, Michigan. But they had a number of outages, and computer problems said that they weren't able to see those problems, and the transmission lines that were left were heating up. And metal, when you heat it up, it loses its strength. And what we say is, for transmission lines, they sag. So here's a transmission line, and it normally goes down a curve like this, which if you remember your statics, it's a catenary curve, and you heat it up, and the line gets like this, and you heat it up some more, and it goes like that. And if you got yourself a little tree down here, before you know it, there is an arc. There's an arc, and you got yourself a fault. You got probably a single line to ground fault, and then the transmission line is taken out. Now, sometimes it burns the tree up, and then when they re-energize the line, it's okay, but sometimes not. And so this is a very dangerous thing. The other thing that's bad about these, not paying attention to the losses, is that as you heat it up and let it sag lower and lower, the metallic goes through a process, and when it starts to cool again, when you take the load off of it, it doesn't go quite back to the original shape. It's now got a permanent little sag to it. You can't do that too many times, and you have to restring the lines. So you don't want to overload the lines, and you need to, so the transmission losses can be destructive. Let's further point out that if it's January and there's a 40-mile-an-hour wind and the temperature is already 10 below zero, you can heat the lines up a little bit, because they're not going to get, the temperature of the line is not going to get too warm. And what will happen in many cases is that the operations group of a power system will take that into account during winter weather, low temperature, high wind. They will change the limits and say, okay, we can push more megawatts on a cold winter windy day than we can on a, and then they'll lower the limit on a day when it's hot, there's no wind, and it's in August, and the system is at near peak load, trying to keep up with air conditioning. That's when it gets very dangerous, because the weather's already hot, and now that's when you do not want to overload the line. Okay, so losses. We're going to talk mainly at this point just about the economics of losses. So you have generators here. Now I'm going to show them on separate buses, although we're going to put a line, make them all interconnected. So And we're going to make this guy, because this is Wallenberg's very simple power system, and we've got loads out here, okay? And we have to realize that all of those lines, all of these lines, I'm just going to put some little red marks around them. They all are contributing to the losses, okay? Even though the load is all spread out and so forth. That's it. So we have P1 to, let's say in this case P3. We have, and I'll just combine it here to P load, and we'll draw a big arrow like that and call it P loss. Now, eventually we're going to get to talk about power flows. Those of you that are mechanical engineering background and or some, you're electrical engineers, but you have not had courses in power system analysis. When we get to there, I will try to remind you that you need to get some texts. Dr. Mohan's book that we use in the 4721 is the best source I know. Just go get the book and read up on power flows. All right. So now we want to say that the sum of the P sub I equals 1 to 3 is equal to P load, like we did before, plus P loss. And the problem is that this is variable. It is not a fixed number. We will do some problem solves where we assume it's just a number, but generally P loss is a function of the sum of the I squared R loss, I squared R, over all transmission lines. Okay? I once had a long argument with a guy about corona losses, and that is not something that we're gonna get into. It's not that big, but I squared R is the problem that we're worried about. And so if this is the current, we call that line here, then an I line is a function of how we generate. So if you take our picture up here and you run a lot of the power for these loads out of P1, well, there's a lot of current coming out of these two lines up here and here. If, on the other hand, most of the power is out of P3, well, the losses are down here and here. And so we need to realize that the losses depend on how we're loading up the system. And so we've created a nonlinear problem that we have to get into. Okay. By the way, thanks to Eric, we discovered that the files I put into the drive for the the problem session on Tuesday, the 24th, those files disappeared. And I've called the IT people. They said they would get back to me. Right now they can't talk to me. The phone is off during the class. But hopefully I can get him to tell me what on earth is happening and I can start putting that back up. But there's a video for the Tuesday lecture. And there is a PowerPoint, not a PowerPoint, a PDF for the scanned copy of the notes. I certainly hope that we don't have a permanent problem that has to do with the size of the video. If that gets to be the case, we may have to use something other than Google Drive. But it really is convenient. I don't want to do anything different. Okay, so now we're gonna set the problem solution up as follows, and we're going to say minimize back to economic dispatch the sum of the FI, PI, just like we had before, I equals 1 to 3, and we're going to say subject to our constraint is now, and I'm going to write it this way, P load, which is just a constant, plus P loss, which in reality is a function of P1, P2, P3, and P load minus the sum of PI equals 0. So we have this and believe me, this loss is not a linear relationship. It's a non-linear. It's a at the least, it's a quadratic function. There's a very modern, very old representation of losses that used something called the B matrix, which I will be honest. This is what I learned when I was actually a master's degree student at the power program at Rensselaer Polytechnic Institute in the 60s, and the B matrix was as much art as it was science, to be honest. But it was what we had. You wanted to do it that way. Now, what we have now are power flows. We can do a much better analysis with power flows. So, in any event, we will get into this, and later on I will bring this up when we get into the power flow chapter, so that we can talk about, well, what is this? How do you do this? But here's the thing. For now, I'm going to go ahead and we're going to say, okay, now like I did in the first beginning of the chapter, I'm going to say this is Fi Pi plus lambda times P load. And I'm just going to write it as P loss minus the sum PI. I'm going to ignore the generator limits for now, like we did earlier. And when you do this, dL dP equals dFi dPi minus lambda times 1 minus dP loss dPi equals 0. So this term that we've introduced, it's interesting. Again, historically, we didn't have the economists to guide us, so to speak. So we adopted the term incremental loss. And the answer is that it could be called marginal loss. I mean, strictly speaking, it's a derivative, so it should be called. But we're going to stick the term that's used most of the time is incremental loss. Let me push the paper here and say what is dP loss dPi, and I'm going to say that if I increase Pi, and I go Pi to Pi plus delta Pi, if I don't change the losses, well, I can't just increase the power on one generator. If I do, we have violated our load plus generator plus. Let me pull it back. If I just increase it on one, then this equation P load plus P loss minus this equals 0 is no longer in force. In other words, where our load generation balance has gone haywire. So I've got to compensate for that. And I'm going to assume that there's another generator. We will get into this in the power flow chapter. Another generator called the reference. Pref equals Pref minus delta Pref. And it changes downward just enough. Now, are they the same? Well, they would be if the losses didn't change. But in any event, this represents the limit as delta P loss divided by delta PI. As you remember your calculus, as you make that delta PI change. So it's the change in losses as I increase PI, just a small amount. And I'm making a compensating change on this over here. The original B matrix methodology did it slightly differently. It said, okay, if I increase PI to delta PI, and then I let all the load go up, so that the sum of the increase on all the load was exactly equal to the PI, again, adjusting for the loss change, then that's a different way of looking at it. And you can reconcile these two with each other. Not a big deal. The B matrix is virtually disappeared. We used to carry it in the textbook. I don't think we even have it anymore. We used to carry it in an appendix, and I may have referred to it or given an example of one, but to my knowledge, it's not used. But I have to tell you, engineers in the 1930s, 40s, 50s, and 60s spent a lot of time with that matrix. All right, so now we have this equation again, that dF sub I, dP sub I equal, let me write it this way, equals lambda times 1 minus dP loss dPi. Okay, I moved this over to the other side, and this is for all I equals 1, 2, 3. And P1 plus P2 plus P3 must equal P load plus P loss. Okay, so all I have to do is find the solution for that. And the next thing then that we want to do is we want to see what to do, how to make this happen. But I want to emphasize that what we do is we say, well, we're going to take dFi dPi equals lambda times 1 minus dP loss dPi, okay? And I'm going to divide. I was once acting as an expert witness in a court case involving a large company in Florida, and I stood in court and I had to try to explain incremental losses to a jury. Number one, the jury was half asleep. They were bored out of their minds. Number two, the jury, the juries are just common folks, common people from America. People, I won't say off the street, but literally they're housewives, people who are school teachers, all the way up to doctors and lawyers and engineers. But they probably don't know what a derivative is or what is a power system or an increment. I had to explain that. I think they were as bored and half asleep when I got done as they were at the beginning. But anyway, you guys are all brilliant power system analysis people, so otherwise you wouldn't be taking this course, right? Anyway, what I'm going to do now is I'm going to state that this is called a penalty factor. Okay, now notice that if the dP loss dPi is positive, if this is a positive number, so if dP loss dPi is greater than 0, then 1 over 1 minus dP loss dPi is greater than 1. Okay, because if this is positive, then it subtracts from 1 here, so you get a number smaller than 1. And these numbers are very, very small. Okay, so we're not talking about numbers up around 1 or 2 or so. We're talking about 0.1, 0.0001, etc. We're talking very small numbers. But it subtracts from this, and you divide that into 1, and you get a number greater than 1. Well, oh goody, I've got a cost function here, and it equals lambda, and now I am multiplying it by a number greater than 1. And what that does, it makes Fi of Pi look more expensive. We'll put that in caps. Makes it look more expensive because it multiplies in the same way that a fuel cost would. So it's like saying, okay, here's your fuel cost, and let's see, I'm going to multiply it by a number that's 1.02. It's 2% larger. The cost of fuel on that generator just went up by 2%, and that is going to make the generator operate at a lower amount compared to all the others because it's making it look more expensive. Furthermore, if dP loss dPi is less than 0, which can happen, and it just depends on the loading, and it means I load the generator up and then I increase the output, other generators decrease, and the overall effect is that losses go down. If this is the case, then 1 over 1 minus dP loss dPi is less than 1. And it makes the generator look less expensive. Okay, it makes it look less expensive. There's an example in the book, and I took great pains to put that example together where you have a generator that sits out here in a long transmission line. You have another generator that sits up here and the load is located right here. And there's losses in this line. And we said, well, let's just do economic dispatch, and then we'll supply the losses from this generator so that if I want a certain amount of power here, then this one supplies that amount plus the losses at this point. And so if I wanted 250 megawatts here and I wanted that out of this generator, in fact these are identical generators in that example. If they're identical generators and I think this is 500 megawatts as I recall, and I want 250 from here and 250 from here. Well, then I got to supply 260 or whatever the losses are here. What's that cost? And you get it. That's worked out for you. And then I went into using the correct analysis like this. To solve these problems, and you're going to do one for homework too. You're going to do one of these for homework too. But to solve, you calculate dP loss, dPi, and then you assume constant. You assume that they're constant, and then in that case, then you just do the 1 over 1 minus dP loss, dPi, dF, dP equals lambda, and you do that for every generator. And again, this is now a constant, and you solve. And then you go back and you use the solution to get new dP loss, dPi for all the generators, and new P loss itself. Now, in the homework problem 2, you're not going to do quite that. You're just going to solve an economic dispatch of a little 3-bus power system, and then we're going to give you some incremental losses, and you assume constant, and solve again, and we'll show you, what is the solution. Now, that's it. I'm not going to make you go any further than that. Later on, we'll give you a piece of code that will take a power system and do an economic dispatch. Then it'll do a power flow, calculate the power flow, and then from the power flow, calculate the losses and the incremental losses, and then come back and do another economic dispatch. So before we'll leave this topic, we'll just point that out. So what you do is you do economic dispatch, and you have P loss and the dP loss, dPi as constants. And maybe you start it out as 0. That's fine. And you get Pi, we'll put a 1 there. That's a solution. And then you solve power flow. When you solve power flow, you get P loss and dPi, dP loss, and we'll put 1s here. These are the initial, but they're now updated. I don't want to do that. I want to call this 2. So we've updated, and now go back and solve again. And you keep going around it. When you update the losses and the incremental losses, you get a new solution, you get a power flow again, and you get new losses and new incremental losses. The process will converge. This is called a relaxation process. We're going to show how to do unit commitment with something called Lagrange relaxation. Relaxation is just we know that this is a variable, but we're going to just hold it constant while we do this other thing, and we'll come back. And it's used all the time, okay? So these start out to be constants. We get new values, and we feed the new values over, and we solve it again. And if you're doing economic dispatch on a power system, without using a very elaborate optimal power flow, this process is basically the one that you would use. If you're a small regional system and you don't have a lot of transmission problems, this works fine. Okay, so that's transmission losses. Now, I'm going to start out with an example that we put in the book. And years ago I was doing some lectures, and I wanted the simple, easiest, and the professor thinks it's simple, and the students roll their eyes and think, oh yeah. or as my kids always used to say, yeah, Dad, yeah, right. Meaning, it's not simple for us, it's simple for you. But I think it's simple. I wanted a simple example that will show the concept of locational marginal price. I'm not going to write it all out again. LMPs. And we're going to introduce auctions. What's an auction? My son and I enjoy watching programs on cable television about automobiles. There's a fellow that has a program called Chasing Classic Cars, and he goes around and he gets people. They tell him, hey, we've got this old Model T Ford, or we've got this old Pierce Arrow, or we've got a very fancy Ferrari that my father bought 30 years ago, but it's been sitting in the barn for 20 years. Usually that means that mice have infested the whole thing and are still living in the glove compartment and everything. Anyway, he pulls these cars, buys them, takes them back to his shop, fixes them up. Okay, so now I've got a 30-year-old Ferrari something or other. How much is it worth? Well, and the answer is when there's no, when it's not something that's currently in the marketplace being sold every day. So if I want to know, well, what's a 60-inch 4G television set worth? I can look in Best Buy store or I can look at Amazon and I get a price. There it is. That's what they'll sell it to you for. That's the price. Maybe you can go on eBay and you can get a little different, but let's not talk about eBay because that's a. But so you when it's not in the marketplace, here's this old 30-year-old Ferrari, and what's it worth? And what you do is you take it to an auction, and the idea is to see if what it's worth is what people will pay for it. So when we don't know a price for something, we take it to an auction. Now, at these auctions for the cars, if he wants, he can set a price that says, okay, if somebody offers me, and believe me, these old sports cars, especially the real valuable ones, they'll go for a couple $100,000. He'll say, I want a base price or I forget the name. Anyway, he has a price. If it doesn't get $175,000, then I'm not selling it. And the auctioneer doesn't like that because he wants it to sell so he gets his cut. But and then people start bidding. And we'll open the bidding with $100,000. 110, do I hear 110, 115, and on it goes. And if it makes his 175, maybe it goes up to 190-some thousand, they yell sold, and they ram the gavel down on the table, bang, sold. Well, that's because they do it that way because nobody knows. Sometimes it just, as he finds out, it depends. He said, well, there's not a lot of bidders here today, and so he doesn't get the bid. So auctions are done when we can't determine the price from a catalog or from the internet. Well, and we'll come back to this maybe a little bit more next week. But the idea is, let's say I have a generator 1, and I'm going to give it some characteristic. I'm going to have 2 segments like this, A and B. Okay, and you notice that the price gets higher. So here's the cost, dollars per hour, and this is P. And let's see, this break point is 400, and let's say this one goes all the way up to 800. Please don't hold me to really well-drawn graphs and so forth. And the slope here is 5. And this is called segment A, and let me put this up. This is segment B, and B has a cost of $750. I have another generator that's a smaller generator that goes 200, 400, and it has 2 segments, and this one C and D, and C has a cost of 6.5, and this one has a cost of 8. Now, this is how we would do this problem if the problem were set up. I'll leave that on there for just another couple seconds. So once again, I have 4 segments. A has a slope of 5. B has 750. C is 6.5, and D is 8. This is an engineered problem. I purposely, and you got to show the decimal points here. 5.00, 750, 6.50, and 8.00. So the cost goes up. A is lowest, then C, then B, then D. Okay? Now, what we're going to say is, first of all, in the absence of any other restraints, there's a simple way to do economic dispatch for this thing, and that is economic dispatch. Load the lowest cost generation segment until exhausted. Load the next segment in cost, the next higher cost, etc. So I load the lowest, then I load the next one, then I load the next one, until I'm done. So, without regard, let's assume for argument that we've got these generators and they're all connected just like this. Boop, 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 boop. And we're going to say that this is 900 megawatts. And here is P1, here is P2. So I'm not worried about transmission lines and so forth. So I'm gonna take and I'm gonna order these segments up as follows. Cost. Here we'll put a table. Cost. We'll put segment, the label, and we'll put the megawatts that it can supply. So A. I'm sorry. This is A, and it's a cost of 5.0, and it can go up to 400 megawatts. B has a cost of, nope, the next in order is not B, it's C, so I should put C here. C is 6.50, and he has a capacity of, 200. Then the next one is B at 7.50, and he has a capacity of 800, and then A, B, C, and D has a cost of 8.0, and he has a cost of 400. Okay, so ascending cost, cheapest, next cheapest, etc., up to the top in cost. Okay, now you want to back up a minute here and say, well, yeah, this works for segments. Remember our segmented LP? Well, if I just take any quadratic function, I can break it into 5 or 10 segments. Boom! I can build a table like this and do the calculation. Okay, so I want to get 900 megawatts. How do I get 900 megawatts? I go in here and I say, okay, we're going to buy all 400 by 400. Okay, so that leaves 500 remain. Good. Come to the next one. Buy 200. So now I have 300 remain. So now I'm just going to buy 300 here, and I'm done. Now, I bought 0 from here, and out here I've used 300, but I still have 500 I could buy from the 751. Okay? Now, those of you that have had economics courses, you know where I'm going with it. Well, maybe you don't know where I'm going, but let's say now along comes somebody and they want to add 1 more megawatt to this. 1 megawatt. How much is that going to cost? So how much to increase the load by 1 megawatt? Oh boy. If I go back up here, I'll just slide this table back. Well, I still have 500 more sitting there that I haven't bought out of this segment B. So I'm going to buy an additional one out of B, and I still don't have to touch D. And so I get an answer. I buy the 1 megawatt from segment B for 7.50. Now, 7.50 is called the clearing price. If you go back to the auction, that's the price where the auction said we were done. We bought the 750. It is also the LMP at our bus is 7.50 because it represents the cost of adding 1 megawatt. If I add 1 megawatt, how much is it going to cost me? And that's the way you always want to think of it that way. What is the cost of adding 1 megawatt? In this case, I've got a single bus. Well, all right. Now I'm going to mess it all up here. Let's see if I... If I'm gonna do this now I'm gonna make the problem a little bit, but actually a lot more complex. And I'm gonna do this. Here's 1, and here's 2. So here's P1, P2. This load is 500 megawatts, and I have a load here. I used to just make the loads a little arrow, and then I thought, we're going to put a little box there that represents the load. So here's 200. So these are the loads, here and here, and here's the generation. But the solution is the same as long as I tell you that I can put whatever I want over the transmission line. So let's now, I'll redraw this on the next page. Let's go to the next page. And so here we are. $500 and $200. Here's 1 and here's 2. Now, the first thing that we're going to do is we're going to start out and say, all right, look, first of all, I'm going to try to buy 500 megawatts, okay? Well, I'm going to start with the cheapest. So, supply 500 at, we're going to call this bus 1 and bus 2. At bus 1. Well, I'm going to buy 400 from segment A at 5.00. Okay, in fact, that's all of it. That's all I can get. And I could go to number to the next segment. I could go to segment B, but I've got a transmission line. And the guy over here says, wait a minute, don't buy the power at 750. I'll sell you from my first segment, segment C, I'll sell you power at 650. Now, it's always the last price. So he gets the other 100 megawatts from segment C on bus 2 at 6.5. So, we're now shipping 100 this way. Okay, along comes the second generator. And we say that this so far is the clearing price is 650 for that generator. We're not done, however. We're not done. You've got to do the whole problem before you get the final answer. So I've got my 500 for the first load. Now the second load. Well, I can buy another 100 from segment C, bus 2, at 6.5, okay? And now I've got to get 300 more. I've got to get 300 more. Well, I go to back to the market and I say, okay, I need 300 megawatts, and I love to think of the fact that there's a guy sitting at a desk with a telephone here, and he's talking to these loads. This is a marketplace. There's a guy here, and the guy says, I need 300 megawatts. This guy says, okay, I've got segment B at 7.5. This guy says, I've got segment D at 8.0. Back to this guy, because it's cheaper. So he buys 300 from segment B, bus 1 at 7.5. Okay, and that's it. Now we're gonna play with this for a while because we want to see that this is the LMP at both buses, and I will show you that in a minute. LMP for bus 1 and bus 2. And what do I mean by that? Locational marginal price at a bus. Now it's the word locational comes in there for a reason. Let's draw our power flow up here. There's actually 300 going this way from that segment. So there's a net of 200 going in that direction. Okay? 200 megawatts going in that direction. And let's come back and look at locational marginal price. Remember, we have our little switch over here with an additional 1 megawatt. Same thing here. We have a switch 1 megawatt. Okay. What if I want to buy a single megawatt from here for this guy, given the loading, and so this guy is already putting out 400 from A, and he's putting out 300 from B. So his net output is 700 into the system, and 500 of it goes into the load, 200 of it goes over the transmission line, and over here he is supplying from segment C 100, and he's also supplying the other 100 from C, and he's that's it. So he's supplying 200 here, and the 200 from the transmission line gives me the 400 down here. This is supposed to be 400. So this guy is supplying 700 of the total. This guy's supplying only 200. 200 is flowing across here. If I want to add 1 megawatt, well, it's pretty obvious here. I'm going to buy it from here because why? Well, again, at this point, I could get 1 megawatt from B at 7.5, or I could get 1 megawatt from D. Remember my high price one here at 8.0. Well, I'm going to buy this one. What about this guy here? I could buy 1 megawatt from B at 750. It's the same thing. 1 megawatt from D, if I wanted to, at 8.0. So I have the same situation. Either of these buses will pull it from that segment B at 750. So therefore, LMP1 equals 7.5, LMP2 equals 7.5. Now, we have ignored losses in this thing. When we get to optimal power flow analysis, we're going to find out that these locational prices have to take account of the losses. If you're ignoring losses and you see equal LMP, then you know that there's no limiting taking place in the transmission system. We'll see that in a couple seconds here, but just so that you notice that. All right, now I'm going to throw one more complexity into this problem. A line from bus 1 to bus 2 has a max of 100 megawatts. This now greatly complicates this problem. It greatly complicates the power system markets because they don't have an infinite ability to move power around at any instant. If certain generators are dumping their power at a very low price, maybe that other generators can't get to it because the transmission will not allow them to push the power across the system. So now we have a limit on there. Let's see if we can do this without, so there's 500 here on bus 1, and there's 400 here on bus 2. So we have A at 5.0, B at 750, and this can go to 400, this can go to what? Another 400, if you will, just the segment itself. This one has got C is at 6.5, and it's got 200 megawatts. I gotta go back and look. 200. And this one, D, has it at 8.0. And that's another 200. Okay, now, but remember now that this one has a maximum of 100. Remember my discussion of the fact that if you load the power transmission up beyond what it's designed, the lines heat up. It's the same principle as an electric toaster or your electric stove at home. You push current through a resistance, and it heats up. Now the stove or the toaster is designed to heat up a certain amount with current from the wall, from the plug. Power system is the same thing. So you don't want to push too much current through because the line will begin to sag, and you can damage the line and or cause it to sag so much that it arcs to the ground, causing what we call a ground fault. All right, well here I am now, and I got a maximum of 100. Let's go through the same process again of loading this up. And you remember that when I did it this last time. So I'll start out and I'll say, okay, I'm gonna fill the order for the 500 megawatts at bus 1. And I'm going to start out, I'm going to say 400 from segment A. I mean, that's easy because I'm not even going, I'm just coming from the generator right into the load, and there's nothing on the transmission line. So that's at 5.0. And then I'm going to buy 100. The next cheapest is over here on C from segment C at 6.5, which is from bus 2, and I'm done. There's 500, and I've now got 100, and it's just sitting at its max. Okay, it's just sitting at its max. Okay, we're good. Let's go to the next one. Now I'm going to fill the order. Let me do this on the starting on the next page. I'll push this up a little bit here. Now let's say fill order for the 400 megawatts at bus 2. All right, so I'm going to start out the same way I did before. I'm going to say, well, I'll buy the remaining 100 megawatts from segment C at 6.5. Doesn't load the transmission line. It just comes out of here and into the load. Good. We're okay. But now you've got 300 more. Okay. All right. So you've got 300 more, and so he puts an order in for 300. He tries to buy 300 from segment B at 7.5. Now remember that when he does that, okay, he gets a reversal of flow of 200. Okay. I'm sorry. He gets an order for 300, which would result in a flow of 200. And the transmission people are screaming, saying, no, you can't put 200 megawatts on that line. It's 100. And by the way, Normally, you think of a transmission line as being a maximum in is the same number no matter which direction it's going into. If you get into reactive power effects, that could change. But in our example here, it's 100 going 1 to 2 or 2 to 1. So we can't buy it. The answer is no. You say, okay, well, what can I do? Well, I'll buy 200 from segment B at 750, and that's okay. And I now have my loading at that point. I should have just kept redrawing this thing. I've now got 100 going this way and 200 going that way. That's it. That's it. So he is supplying what? He's supplying up here 400 at 5, and then he wanted to get the remainder from B at 300, but he can only get 200. This is from A, this is from B. So he gets 600, of which 500 is going here, and he ends up, because this adds algebraically, so he ends up with 100 there, and that's it. He can't get any more of the cheap power from me. And now he's only fulfilled this 400 order. So this one is out. He can get 100 and he gets 200. He's only got 300. So then he has to buy 100 megawatts from the dreaded expensive segment D at 8.0. And so now he's sitting here, and we've got his 400. You got 100 from C, 200 from B. That's coming across. That's it. And so this is limiting, and now he buys the other 100 at 2. Now let's go back to our analysis now with the switch. Whoop! Drew the switch the wrong way. Here it is. Here's my little 1 megawatt. And I've got a switch here, and I'm going to try this 1 megawatt. Okay. If I go to here and I add 1 megawatt, well, that comes from B. From B. Now, if you look at it, you say, well, what if he bought it through the transmission? 1 megawatt reversed this, and so on and so on. It wouldn't make any difference. And so the cost is $750. So LMP at 1 equals 7.5. Back here, 1 megawatt has to come from additional out of this D. I can't push another 1 megawatt through the system. So now from segment D at 8, so the LMP2 is equal to 8.0. Now what we're showing here, I'm sorry, I'm drawing and I'm not paying attention to the screen. Let me go back over it again. We've settled on the bus 2 bought 100 megawatts from his own generator. That's all he had on segment C. He bought 200 from B back over, and that exhausted all the power he could transfer across. Then he bought another 100, and so that gave him a total of 400. The last one he bought was at 8. And so the 1 megawatt on bus 1 cost him $750. The 1 megawatt at bus 2 has to come from this one because that transmission line says nothing to it, no more. It's at 8. So we now show that with transmission limits affecting us, the locational price is different. The locational price is different. And the flow on a constrained line, and that's what we have there. That line is constrained. is always from the lower LMP to the higher. Okay, so we've now got this example. Now, this kind of thing, we're gonna see this later on, and especially at the end of the course, where we deal with these locational marginal price, how you operate a large auction, how you do the market analysis. And we're going to give you a homework problem. Let me see. This is page 8. I thought about numbering the pages ahead of time so I don't have to go back and forth. But then I thought, if I need to pull a piece of paper out, then all of remaining. Okay, so homework 2. You've got that MATLAB program. And you're going to do using LP. So that's there to show, and I've got lots of things that you're going to do. So that's problem 1. And then problem 2 is you're going to do an economic dispatch on 3 generators. And then you're going to do an economic dispatch with DP loss, DPI. And you're just going to do it once. You're not going to try to come back and recalculate. We didn't show you how to do that, so we'll assume they're constant. And so with loss, which I think was 3%, I said make it equal to 3. So you're going to resolve the economic dispatch. I want you to be careful of generator limits. So there's when the professor says watch this, watch generator limits, the P minus and the P plus. Boom. So be careful of those in that problem. Okay? We are working on getting things into the Google Drive. If it doesn't work properly, if we can't get them into the Google Drive, I will just start using Dropbox. I will give you guys an open directory on my own private Dropbox, and we'll just use it the same way. If at least in Dropbox, when I load up a video file, it doesn't do anything to it. It just puts it there. Dropbox is just like a big hard drive. I got into it because the university, I had a project with a bunch of people and they wanted me to use Dropbox. Fine, I got into Dropbox and I discovered what an absolute unbelievable joy it was to work at home when I was writing the book. And then to go to school, to go to the university and bring up my computer there with the Dropbox account, and there is the same thing I was working on. It's all the same. And get done doing some work, maybe some simulations with MATLAB at the university, and come home that evening or the weekend, and I'm working on the book again, and everything is right in front of me. Then Dropbox came along and said, 100 G bytes is really not that big. How about 1 terabyte for $100 a year? And I said, absolutely. So actually, I still have about 300 G bytes. No, about 700 G bytes unused. Should be enough. So we may, if I can't, then I will just open up an EE5721 directory on Dropbox. I will let you know tomorrow if the IT people and I can get that straight. But I don't know. I just I'd hope that this Google Drive. Some of you will get to know me after a while. You'll know that I'm a very conservative person politically, and one of the things I don't like about dealing with Google is that they have certain rules, they have certain regulations, and if you don't do something right, then they make it hard for you. Dropbox says, here it is. There's 1 terabyte Put anything where you want it. Doesn't matter as long as you go up on the 1 terabyte, which we're not going to do. So we might end up getting off of the Google Drive altogether. I'd rather not. So hopefully we can figure that out, and we'll hit you all with an email. I'm warning everybody. I'm going to use email to talk to you. Read your emails. Look for emails from me. Your first homework is due tomorrow. The afternoon, late afternoon at 5104, he's not doctor yet, Dr. Choi, but RTA, Hunjin Choi, okay? And if you need help from me, some of you have been emailing me, that's good too, okay? Exit full screen, and we shall... I'm going to leave the meeting and end the meeting. So we will see you next week on Tuesday.